Hi everybody, this is Dr. Nigro here with the Chem Calculations video. This one's going to focus on specific heat as part of our unit on thermochemistry. All right, well up first, what is specific heat? All right, well remember specific heat is a physical property and it's a measure of an object's ability to absorb energy without changing temperature. All right, and as I said, this is a physical property. So you need to know what your object is made of in terms of its chemical makeup. All right. Now, the formula for specific heat is SH equals Q, which is heat, divided by the mass of your substance times that temperature change. All right, so based on this formula, we have a couple of relationships. All right, so for example, if we're looking at a substance with a high specific heat, then what that tells me about that substance is that you're going to need to add in a lot of energy, all right, if you want to change that temperature, all right, because that high specific heat value tells me that that temperature change is going to be pretty low. All right, so that means that the specific heat value and the energy that that object can absorb are directly related to each other, whereas the specific heat and the temperature change are indirectly related to each other. All right, we don't really talk about specific heat versus mass because changing the specific heat or looking at different specific heat values does not actually affect matter or the amount of matter itself. All right. We can, however, if we know the specific heat of a substance, we can relate the energy and the temperature change. So, for example, if we know a substance's specific heat, the more energy that we put in, the greater that temperature change is going to be. So, this is a direct relationship as well. All right. Now, one place we can talk about mass is its relationship to the energy being absorbed or the temperature change. All right. So if we have a substance and it has a lot of mass, then it's going to require a lot of energy. So this again is going to be a direct relationship. All right. If we have a substance with a lot of mass and we're putting in the same amount of energy, all right, then as the mass of that substance increases, the temperature change is going to go down because it's going to be able to absorb more and more energy because it's got more and more mass. All right, so we're going to work a couple problems together that look at using this formula for specific heat. I guess I should make a side note over here. All right, in your textbook, sometimes the specific heat variable is listed this way with CP because this specific heat sometimes has the word capacity after it, specific heat capacity. It means the same thing, and it's just kind of your personal preference. I learned it with SH for specific heat, so that's kind of how I teach it. All right, so let's look at problem number one. How much energy is needed to increase the temperature of a 25-gram sample of steel from 25.5 to 45.5 degrees Celsius? The specific heat of steel is 0.466 joules per gram degrees Celsius. All right, so when I work problems based with formulas, I like to list out my variables. So I'm going to have specific heat, energy, and delta T, but I like to list it as T initial and T final, and then mass. All right, so my specific heat is given as 466, and that's joules, grams, degrees Celsius. Energy is my unknown. The initial temperature is 25.5 degrees Celsius. The final temperature is 45.5 degrees Celsius, and our sample has a mass of 25 grams. All right, our temperature values can be used to calculate delta T. Remember, that's T final minus T initial. So in this case, delta T is going to be 20 degrees Celsius. All right, so we have everything we need. We look at our formula. We have specific heat is equal to Q divided by mass times delta T. Now I'm solving for Q, so I'm going to rearrange. So energy is going to be equal to specific heat times mass times delta T. All right, so we plug things in, 0.466, and that's joules, grams, degrees Celsius, times our mass of 25 grams, times our temperature change of 20 degrees Celsius. All right, if we look, the Celsius is going to cancel, the grams are going to cancel. We're going to be left with joules, which is our energy unit. And once we plug everything in, we find that when we add in energy to this sample, we're going to need 233 joules worth of energy to get the temperature of 25 grams of steel to increase by 20 degrees. All right, let's slide down to number 2. This time it's asking what is the specific heat of graphite if the absorption of 150 joules increases the temperature of a 15.25 gram sample by 7.5 degrees Celsius. So again, specific heat, we've got Q, mass. This time it doesn't give us an initial and final temperature, it just tells us the temperature change, so delta T. Our specific heat is unknown. We have 150 joules of energy being absorbed by 15.25 grams of a sample, and that temperature goes up by 7.5 degrees Celsius. All right, so our formula, specific heat equals Q divided by mass times delta T. We don't need to rearrange because specific heats are unknown, so we put in 150 joules, and then underneath 15.25 grams and 7.5 degrees Celsius. Plug all that into our calculator, and we find that the specific heat of graphite is 1.31 joules times grams degrees Celsius. All right, now if we compare this specific heat to that of our substance up in problem 1, steel, which has a specific heat of 4.66, we can see that the specific heat of graphite is greater. And what that means in terms of energy is that it's able to absorb more energy than steel, but maintain its temperature. All right. Finally, number 3, how many grams of water can be heated from 20 to 75 degrees Celsius using 12,500 joules of energy. All right, so specific heat, energy, mass, and this time we do have an initial and a final temperature, so I'm going to list them separately. All right, let's see what we know. Well, we know that the initial temperature is 20 degrees Celsius, and it ends at 75 degrees Celsius. We're going to input 12,500 joules of energy, and we're asked for mass, which means we should know the specific heat. And this is one of those values that is a good idea to know. So just like knowing the density of water is very helpful, knowing the specific heat of water is also very helpful. It's 4.184 joules grams degree Celsius. So you can see, even compared to graphite from problem number 2, water has a specific heat that's almost 4 times higher. So it's able to absorb almost 4 times more energy than even graphite without changing its temperature. All right, again, we look down at our temperature values. Delta T is T final minus T initial. So in this case, 75 minus 20 is going to give us a temperature change of 55 degrees Celsius. All right, so we look at our formula, specific heat equals Q divided by mass times delta T. All right, this time we're looking for mass, so we rearrange, and mass is going to be equal to Q divided by specific heat times delta T. So now we plug everything in, 12,500 joules divided by 4.184 joules grams degrees Celsius, and our temperature chain of 55 degrees Celsius. So this is going to cancel, the joules will cancel, the gram is in the denominator of the denominator, which makes it flip up, which means mass will have a unit of grams. Plug everything into our calculator, and we find that the mass of this substance must have been 54.3 grams. Okay, so those are 3 different problems using the specific heat formula. We solved one where we found the energy, we solved a second where we found the specific heat, and a third where we found the mass. All right, now another problem that comes up a lot is where you want to find either the final or initial temperature. If you run into a problem like that, you're going to solve for delta T in your formula, and then you're going to plug delta T into your delta T formula. You'll have this number and then one of these two, and then you solve for the unknown. Okay? All right, I hope that was helpful.